The previous videos showed different ways to model uncertain input data, variable output data, and different types of probabilistic methods. They are essential in calculating a probabilistic power flow to understand the diversity of power system operating conditions. In this video, the application of non-sequential Monte Carlo method is studied, evaluated the relevance of its implementation steps. Recall that the non-sequential Monte Carlo method for probabilistic power flow estimates how a power system behaves under uncertainty by looking at many randomly generated independent scenarios for inputs like load or renewable generation. Unlike sequential methods, it does not consider time order, focusing instead on the range of possible system conditions, that is, the sample space. The input data are the uncertain variables described by the probabilistic distribution functions, representing the natural variability of demand, generation, and other factors. The output data are probabilistic measures of system performance, such as expected voltages, line flows, losses, and the likelihood that limits are exceeded. And the main steps of non-sequential Monte Carlo involve first, define uncertainties and the distribution. Next, randomly generate many dependent scenarios representing different possible system conditions. Next, run deterministic power flow for each scenario. Finally, combine results to compute probabilistic statistics like expected values, variances, or risk metrics. Non-sequential Monte Carlo is simple and flexible, giving a broad picture of system risks and performance under uncertainty. Its main trade-off is that achieving reliable results often requires many simulations, which can be computationally intensive. In the non-sequential Monte Carlo method, each randomly sampled operating condition X, that is, a specific combination of load and demand drawn from the probability distributions, is passed through a deterministic power flow model, producing a corresponding system response H of X, like bus voltages, line flows. Repeating this process many times generates a set of Monte Carlo samples of system performance, which collectively approximate the probability distribution of the outputs. From this sample, probabilistic distribution functions and cumulative distribution functions of performance variables can be constructed, provided a complete probabilistic picture of system behavior. For example, the risk of undervoltage at a bus can be estimated using cumulative distribution function of its voltage magnitude by evaluating the probability that the voltage falls below a specific limit. In short, non-sequential Monte Carlo maps uncertain inputs into system responses and uses repeated samples to transform variability into quantifiable risk and probability measures. The law of large numbers is fundamental to the numerical trustworthiness of the Monte Carlo method in probabilistic power flow. It states that as the number of random samples increases, the estimated results like mean voltages, probabilities of violations, converge to their true probabilistic values. In practice, this means that by simulating many independent conditions, the computed probabilistic distribution functions and cumulative distribution functions and risk metrics become increasingly accurate and stable. However, it also implies that a trade-off of achieving high accuracy might require a large number of simulations, leading to higher computational effort. In short, the law of large numbers ensures that Monte Carlo estimates trustworthiness, provided that enough samples are used. In the non-sequential Monte Carlo method, for probabilistic power flow, a stopping criterion is essential to determine when enough simulations have been performed to obtain reliable and stable results without unnecessary computational effort. Since accuracy improves gradually with more samples, a stopping rule ensures a balance between precision and efficiency. A common criterion is to monitor the ratio between the standard deviation and the expected value of an output variable. That means the coefficient of variation. When this ratio stabilizes or falls below a predefined threshold, it indicates that the estimate has sufficiently converged. Another approach assumes that the statistical error of the estimates follows a Gaussian distribution, allowing convergence to be assessed using confidence intervals. Summarizing, stopping criteria ensure that Monte Carlo results are statistically meaningful while avoiding excessive computation. To conclude, in this video, the application of non-sequential Monte Carlo method to probabilistic power flow calculation is studied. The importance of the low or large numbers and the importance of defining a proper stopping criterion was emphasized. This ensures results with the most statistical value.